Hi, y'all. So today I'm going to do the group work. This is for chapter 16 for the Solomons, but it's chapter 19 for Klein. And it really is like carbonyl chemistry and the chemistry of carbonyl. So the first question is to draw a flowchart of the relevant reaction. So that's something that we've done in class and that I really think is more beneficial for you to do. That's basically like a space for you to organize your notes and make sense of everything. But one thing I do want to talk about, and I've talked about this a lot before, but if you have a ketone and a nucleophile in any setting, this is partial positive. As long as there's not an acid-base reaction that could happen first, this is going to be partially positive. The nucleophile will attack and kick this up. And it's going to make for O minus, a nucleophile, and then your existing R groups will be there. If you add acid, it will become an alcohol. And this is very normal. This is what you're going to see a bunch in this chapter. The additional thing that you'll see in this chapter is then an elimination reaction. You've seen this before, where if something can happen to make a double bond fill in here, you'll get this leaving group to leave, and you'll just have your nucleophile stay behind. This would be an enamine, or if there's a lone pair here, it can fill in, and that leaving group can leave, and you can get an elimination reaction where there's a double bond to your nucleophile. So that's taking this reaction one step further. You turn this into a good leaving group by protonating it, and then you can do an elimination reaction. But all this is stuff that you've already seen before. It's just stuff you've seen before in kind of a new environment. So that's going to be the big basis of this chapter is you'll have OH with a nucleophile, and a lot of times that nucleophile will have two lone pairs, so you'll have O minus and then a nucleophile with a lone pair still there. Might also have a hydrogen that can get stolen, or there'll be a hydrogen in the environment. So say this formed, like if it's nitrogen, this proton can transfer and you can get OH with your nucleophile. It's lone pairs. You can protonate that. And that's what we've seen multiple times before, but you can protonate that again if there's H plus in the environment, OH2 plus. That's now a good leaving group. And then you have lone pairs on your nucleophile that can come in and fill in and kick this out, giving you this kind of group. Or the other thing that could happen is a base could be abstract a hydrogen from here or here, just like eliminations, acid catalyzed dehydration eliminations you've seen before. Make a double bond and kick that out. So that's what we're going to see over and over in this chapter. So I just wanted y'all to kind of be on the lookout for that. So this first one is not going to be any exception. Don't worry too much about like this name formation and then the imine. Don't let that scare you if you feel like you're not like, oh, I don't 100% know what those are. Don't let that, freak you out too much. Sorry, the sun was in my eyes, so I just scoot away. Don't let that freak you out too much. Use what you already know. So if you're ever not sure, just use what you already know. And one thing we know is that, one, they've given us the overall reaction. This is an imine reaction. So if you aren't super good on mechanisms, just know that the nitrogen will pop on right there, kick off the oxygen, and whatever the nitrogen had attached to it will stay attached to it. But I do want you to know the mechanism. So we have our nucleophile with a lone pair, and then we have this partial positive center here. Now, I usually just draw the nucleophile attacking first and this kicking up. However, this can be protonated initially in solution. The protonations are kind of murky. It's my preference that I don't care when it gets protonated. You just need to know that it gets protonated. You don't need to know like where it gets protonated from or necessarily when. You just need to know that it gets protonated, because honestly, a lot of when things protonate is all acid-base reactions which occur in equilibrium anyway. So I think any organic chemist wouldn't really argue super hard that a proton transfer needs to happen exactly when. A lot of our proton transfer assumptions come on like based on equilibrium, based on what we know about pKa's, based on what we know about the environment, we think the proton transfer will happen here. But if that's what's getting you mixed up on how to do a mechanism, I don't want you to worry about that. I want you to focus on doing the mechanism. That's what I care about. So the result product of this would be our nitrogens here. It still has its 2 hydrogen attached. It just formed a new bond right there, which means it's positive. And then it also has this group over here, this 5-membered ring. So that's the first step. And honestly, the thing that I normally do at this point is an intramolecular transfer, where that alcohol will get protonated from this positive nitrogen because they're right next to each other anyway. So that would be OH here. And NH, the lone pair has been restored because that came back. And your 5-membered ring. So then the next step, this is the carbonylamine or whatever. But the next step is the imine formation. And with the imine formation, this happens with H plus is going to come attack here. Oh, this is still have the nitrogen here. The oxygen is going to attack the H plus here to protonate again to turn it into a good leaving group. So if you're on exam though and you can't quite remember exactly what happens, just draw what you know and get partial credit points because some points is better than no points. So now this has become a good leaving group, and the lone pair from the amine will come in and kick this out. And you will get, oh no, that's been kicked out. Sorry, I'll start over here. A double bond with your nitrogen. It still has, this lone pair actually formed the bond. Ignore that. I'm sorry, I'm bad at drawing right now. It still has the hydrogen right here. And it's positively charged because there's 4 things bonded to it. So that will get deprotonated and you'll end up with, now it has the lone pair back. And that's how you got the final product. So that is the formation of an imine. And it's basically exactly what we talked about there on the front page. The nucleophile attacks, the carbonyl group kicks up to become an O-. That gets protonated. It gets protonated again to become a good leaving group. And then we essentially have an elimination reaction where that oxygen is being kicked out, the water is lost. And that's what this is referring to right here, is the water being lost. Now, the next question is, how would this be different if it was replaced with a secondary amine? That's enamine formation. And the first step of enamine formation actually would be the same. So this would attack and kick up. Of course, it's the same. It's always the same, right? So we would have our O- and then our nitrogen with the ring around it. I don't know if that's a 6-membered ring. I think it is. And this is positively charged because it has 4 things bonded to it. So I'm going to do the same thing. I'm going to say this is going to get protonated and this is going to come back here. And we'll have OH with N and the 6-membered ring with the lone pairs back. And then from H plus in the solution, it will come and attack this and make this a good leaving group. So then you'll have OH2 plus and your nitrogen. And in this case, actually, it's a little bit more complicated because the nitrogen is going to do the same thing. It'll come in and kick this out, but then you get a positively charged nitrogen, right? Because it's now got 4 things bonded to it. So that's not incredibly happy. So actually, this becomes more acidic because it's not stable the way it is. So this will come take this proton, come up here and kick this out. Just like other elimination reactions that you've seen. It's very similar to other elimination reactions. And I have seen this drawn sometimes where people will draw, instead of like the nitrogen coming back down here on this step, they'll draw the base taking like this hydrogen or this hydrogen, and then double bond never forms. But if that's too confusing, don't worry about it. Sorry, there was a knock on my door, so I kind of lost track of what I was saying there. But I think I was just saying that some people draw this mechanism differently, but I think this is the most similar to the imine formation, and this is similar to an elimination reaction, so that's what I go with. But whatever, I would go with that on your exam because that's what Dr. Corrales also presented. But if you see something else, I don't want you to get too confused. Okay. Let's talk about this next one. Sorry, I have like all my books and stuff on here. The sun's creeping into my room, so I'm like shifting away. Okay. Draw the mechanism of the following reaction. So again, we see the same thing that happens on these reactions over and over, right? So if you have this ketone could protonate, and I think I lost a carbon there. It could go to the OH, leaving a partial positive here. Or you can draw the protonation step afterwards. Either one of those is fine. And then again, the nucleophile is going to attack at that carbonyl carbon, that partial positive. And this attacking itself, it's weird. You've never seen anything like it before, but it's the same thing. The nucleophile is attacking at the carbonyl carbon. So if you don't want to draw the protonation step first, you can draw this happening. Either way, the nucleophile is attacking just the same way it always has. But it gets weird because it's making a ring. So what I always do is number these. Numbering carbons makes it so that you don't lose them and makes it much easier to see. So this, with the oxygen included, would be a 6-membered ring. So before I draw that out, sometimes it helps students to see. It's kind of like there's a bond that forms right here, but we don't have long curvy bonds. It's short bonds. So instead, it would be more appropriate to have a bond that looks like this, right? So this is the bond right here between carbon 6 and this oxygen 1. And there's 1, 2, 3, 4 things in between for a total of 6. So it's a 6-membered ring. So here's carbon 6 right here. It has a methyl and an alcohol. And then 1, 2, 3, 4, 5 other members of the ring. And so that's how we get this structure right here. I have the ring on the bottom side because that's easier to visualize for me, but this is just this flipped over, so it's the same either way. And stereochemistry isn't drawn, so you don't have to worry about that. So that is known as a cyclic hemiacetal. So a hemiacetal, half is hemi, so 1 alcohol and 1 OR. You have that, an alcohol and an OR. It just as happens that the R is attached back here instead of being separate. So this is what's called a cyclic hemiacetal. And I think you'll see more and more of those reactions. One thing I do want to say, though, is they'll form 6-membered rings and they'll form 5-membered rings for cyclic hemiacetals, looking like this. But typically, anything shorter than that, such as like this, I don't know why I did a double bond there. This is unlikely to form because there's a high amount of ring strain. So the carbons there needs to be a total of 5 or 6 members of the ring. You can't have like a 4-membered ring that forms. It's very, very unstable, so it's very unlikely to form. The other thing is I just realized I didn't leave this protonated. So this is initially protonated and then gets deprotonated. That alcohol doesn't lose its hydrogen until it specifically gets deprotonated. So OH. There you go. Okay, next question. This is going to be, again, a very, very similar mechanism. I'm going to draw this sulfur coming, attacking, and kicking this up. You can draw the protonation step happening first. I don't care which one happens first. O minus. And then you have your S. It still has an H on it, so it's positive because it has all these things bonded to it. And then a hydrogen over here. This is positive and this is negative, so there's going to be a proton transfer. It can also come from this H plus in the solution. It's honestly whatever, wherever it comes from, doesn't super matter. And then this reaction wants to happen again, but there's already 5 things bonded to that proton. So this is the thioacetal, and then you'll get the next step, which is the full thioacetal formation. So I'm just redrawing the structure down here. So what will happen is this will take some of the acid that's in solution and protonate itself to become a good leaving group. Just like we saw with imine and enamine formation, this is OH2 plus now. And then your sulfur, this sulfur right here will come and attack and kick this out. And you'll make this left. So you have S, S. This is a methyl group. I don't know why it's like not, I didn't draw it attached fully, but it's just one methyl group there. And an H over here. And then this is still protonated. That will get deprotonated in solution. So it will end up looking like, it'll get deprotonated by probably the water in the solution. And the lone pairs that make up that double bond will come back on the sulfur and make it neutral. And you'll get this thioacetal. And if you react to thioacetal with rainy nickel, it will just get rid of the thioacetal. So usually if you see this followed by, I think it's called a dithiol, followed by rainy nickel, that's a good indication that this ketone's just going away, just like a reduction. For some reason, I really like those reactions, and this is one of my favorite reactions. So yeah. Okay, this next question is a Wittig reaction. I like Wittig reactions. This isn't asked for the mechanism, but I am gonna show you what I do. I usually will line up the oxygen with the pH3. Sometimes it just gets abbreviated as PR3 too. And this is got a phenyl and a hydrogen. And you can draw the box forming and do the whole mechanism, but what I do is just know these are going away and a double bond is forming right here. So a double bond is forming there with this and this and this and this. Boom. Now, that's how I do Wittig reactions. You can do the whole mechanism. I do know the mechanism. I know how to do it, but this is been the easiest way for me to figure out. I just like draw them, line up the oxygen and the phosphorus, right? Yeah, right? I think that's what a P is. And then I put a double bond right there in between those other two things and get rid of these. That's literally what I do whenever I see a Wittig reaction. I think they're kind of fun, but it is just memorizing that I do that with. It's not like knowing the mechanism, but whatever. I just like it, okay? So sue me. And then that's the overall reaction. But there is a nucleophile and an electrophile here. As always, the electrophile is the thing that's going to get attacked. So this this has a state that's known as Zwitter ionic, the Wittig reagent, where actually, because of all these phenyl groups here, if this bond breaks and goes there, the second bond, the pi bond, you can have this structure. And these nucleophiles are what attack here. This negatively charged portion can attack. I think that's right. Hang on. Okay, I'm glad I checked because I actually got this wrong. So actually the arrow goes this way. I'm glad I looked this up. So this forms a carbocation over here, positive, and the single bond, I do that wrong, has a negative lone pair. So sorry for any confusion. Let me get a fresh page and start over for you. I think that will be better. Okay, here we go. I got a fresh page. So what happens is actually these nucleophile, it breaks like this. And then you have this structure. So there's a lone pair on this side with the phenyl and the hydrogen and a positive charge over here. And it lines up like I had drawn in the other video with this oxygen here. And you've got your Oh, I miss that backwards. Sorry. Lines up over here. You've got these and this. So something I want to draw your attention to right now is I line up the oxygen and the phosphorus. There's a resonance structure here too, right? So if you draw this resonance structure, this is O minus. This is plus. So you have your phenyl over here with its 3 R groups, and it's positively charged. And then you have a negative charge on your phenyl over here. And so your carbonyl will come and attack, so this is nucleophilic, but then the oxygen in response will then go and attack the positive charge. So this is your initial nucleophile, and then this is your secondary nucleophile. And that's what forms the box, but again, I just cover it up, like this. So that reaction happens, it forms a box, and then actually that same thing happens again. So I would say that initially this is your electrophile because this is being attacked, and this is your nucleophile. And then on the second step in that mechanism, this is the nucleophile, and it attacks right here on the electrophile. So that's my understanding of this reaction. But I don't think you'll need to know that in depth of what happens. Now, the next question is the reagent stabilized through resonance? If yes, show resonance structures. So I drew this. The Zwitter ionic form is what this is called, where there's a positive and a negative charge coexisting next to each other. And this is definitely stabilized through resonance. It's stabilized on this side because there's so many phenols, but it's also stabilized on the other side. So I'm going to draw this out for you. So if you have this double bond here, and there's double bond here and here and here, this can go here and this can break. And you can get your phosphorus with a double bond, this left this positive, and you have all your phenols here. And then your negative charge would be right here, and then you'd have this, and then you'd have a resonance structure where this comes in. So yes, I agree that this is stabilized by resonance. What type of stereochemistry is expected on the alkene? So we see E stereochemistry, which means opposite, or E for enemies. I really like that. Whoever said that, I spelled opposite wrong there. If there's an electron withdrawing group. And I like that all those, E opposite enemies, I like that. And then Z, I always think ZAME because Z and S kind of look similar, ZAME. If you have anything else, anything other than an electron withdrawing group. And for the product, so I actually, we didn't go over a lot of this when I took OChem originally, so I didn't know this rule until I was sitting in class with y'all the other day. So I would think that this lone pair having the being able to be stabilized by resonance, that this would be an electron donating group. But there is a resonance structure where it's positive as well. If you had this structure, this could go over here and this could come down, and you would get a negative charge here. Phenyl, phenyl, phenyl. This would be negative. And then you'd have a bond to a positive on, well, this would have been filled in. And then you'd have a positive on your benzene ring, like right here. So I'm actually on the fence if this is E or Z, because of that resonance structure. Normally, I would say a benzene ring is going to be neutral or electron, like very lightly electron donating. So based on that, I would say that it would be, this should be anything not electron withdrawing group. I would say it would be Z, but I've kind of gone back and forth on this, so that's something that I may ask Dr. Corrales to address in class, because this is new to me too, and I'm not sure. I think personally I would probably think it would go the other way, but I don't know. So I don't have a firm answer on whether or not this would be E or Z. The product ultimately would be this on one side and a phenyl and a hydrogen on the other. It would either be Z or E. And I don't have a solid answer on that one for you, unfortunately. I just want to be honest, I don't want to confuse you more based on this. And this is not something that I learned until you also learned it in class. And my instinct is to say that this would be Z product, but I don't know for sure on that particular one because of possibility of resonance structures. So I'm going to leave this one by itself. But I will say if this was a nitro, there would be no question. So like if you had started originally with this and your PPH3 with a nitrobenzene or something like strongly electron withdrawing that I knew for sure is electron withdrawing, then I would say this would definitely give you E conformation. But in this one case, I'm kind of on the fence. So I don't know. This next question is, it has a benzyl. So we have PPH3 with a benzyl. So right here, there's a bend. Right? A benzyl has a bend in it. So there's these two, and we know that alkyl groups, this is the bend for benzyl. There's a bend in it, and alkyl groups are electron donating. So this is going to be Z conformation because it's not electron withdrawing. It's electron donating. They give electron groups there. And then our other structure is the same. So I always line up this O, H, and then these would get a double bond between them, and these would get a double bond between them. So we're only looking at this side. And the H's would be on the same side, and then your benzene would be on the same side as your tert-butyl structure. So that would be your answer for that one. Sorry I don't have a satisfying answer. I tried to find a satisfying answer before I started to make this video, but I couldn't come up with something, and unfortunately I'm kind of crunched for time. So I figured I would just leave it open and admit that I didn't know, and hopefully we can circle back around to it in class when I can ask another expert. Okay, so the next questions for each of these, which would be expected to react more rapidly with a nucleophile. So something that's going to react more rapidly with a nucleophile is going to be more electrophilic. And usually electrophiles are more positive, right? So we're looking for something that has the most positive center. And in all of our carbonyl chemistry reactions so far, the positive center has been right here. So we're looking at what's going to make that the most positive. So we're looking at if the things around the positive center are electron drawing or electron donating, electron withdrawing. That's what we're looking for. So both of these phenyl groups would actually do the same amount of, I think they would lightly donate electrons to this positive structure due to resonance. So the only difference is here and here. And actually carbons have more electron density, right? Because this is a carbon with 3 hydrogens. So technically around here, there's 6 electrons in these bonds that could be donated or pulled in there, leaving behind a partial positive. Well, this only has 2 electrons. There's nothing else bonded to it. So it's not able to donate a lot. It's not really doing anything, that hydrogen there. So it's neither electron withdrawing nor electron donating, really. It's kind of just neutral. It's just there. So I would say that this is more stabilized. It has more electron donating groups, which make it less reactive. So this has some electron density that can donate here, and that makes this partial positive a little bit less, right? Like it gets some electron density, and it's still partial positive, but it's a smaller partial positive. This isn't getting any electron density, so it's the same amount of partial positive. Nothing is making that smaller, so this is more positive than the one on the left. So then I will use that same logic on the next one. Which one of these is more positive? So which one of these is more electron donating and which one is more withdrawing? Well, these both have carbons here and here, so that's the same. So I'm looking for differences. And these carbons are surrounded by fluorines and these are surrounded by hydrogens. Again, hydrogens aren't really going to do anything. They're just there. They're not donating, they're not withdrawing, they're just there. They don't have a lot of like pull to give, right? So both of these have a partial positive that the carbon's giving a little to. These hydrogens aren't doing very much else, so this is a slightly stabilized. But over here, these carbons are surrounded by fluorines, and fluorines are significantly withdrawing. So they're going to be pulling electron density away from the carbon, meaning that there's not going to be very much left. This carbon's already going to be partial positive, right? If there's a group of CF3 on a benzene ring, we call that electron withdrawing. So this carbon's already going to be kind of partially positive, so it's not going to have anything left to give to this center carbon that's partially positive. So there's a lot more positivity going on here. So this one is less stable, more reactive. So you kind of have to be able to think through like which one is getting more electrons donated, and for reactivity, that's worse. It's better for energy, it's more stable, but for reactivity, it's not as good. Okay, and now we go into a million different reactions. This is actually some of my favorite parts of organic chemistry, is when you're just like trying to solve a puzzle. So I would say this amine is going to come and attack at the partial positive, because that's what happens. And it looks like it's going to form a ring if it's attacking on itself. So let's make sure that it can even do that. 1, 2, 3, 4, 5. It's a 5-membered ring. So whenever that happens, I actually just go ahead and draw a 5-membered ring. This is 5, O minus, and this is 1, NH2 plus, and 2, 3, 4, 5. Yeah, okay, so this is carbon 5, 4, 3, 2, and 1 was at the nitrogen. This is positive because it has its 2 hydrogens there, and this is negative because, sorry, my light keeps changing as the hours go by. This is negative because when it attacked, it kicked up here. So the first thing I think that's going to happen is we'll get NH. The lone pairs will go back to that nitrogen, and you'll have OH up here. And then because there's H plus in solution, it will protonate again to become a good leaving group. OH2 plus. And then these lone pairs right here will come in and kick up this water, and you end up with nitrogen here with a hydrogen, and that's positively charged, and then that will be deprotonated. So your final structure is an imine, a cyclic imine. If this was on an exam and you knew what would happen, you wouldn't have to go through all those steps, but I actually go through all those steps pretty much every time because I lose carbon so easily, and it's easy to think that you know what's going to happen, but then you get into it and you're like, actually, I don't know what's going to happen or I missed something here. So I always go through all the steps. So you'll see, even though these are the exact same reactions and I could just infer what's going to happen, I'm going to draw it again because it's just easier for me. And I'm even going to label the carbons again. So this is another 5-membered ring. O minus there, the nitrogen's there. So we have 1, 2, 3, 4, 5. And then at carbon 3, we have 2 methyl groups. And at carbon 5, in this case, actually, we also have a methyl group. Now, here's where I will take a shortcut. I'll go ahead and protonate both of these twice, and I'm not going to draw out all of the 2 protonations that happen there, just because that makes my life a little bit easier. But I still draw out the arrow attacking. I number my carbons to make sure everything's right, and then I'll put my lone here, and kick this out, and that will end up with a methyl group there, but this left. So a methyl group right there, and an NH with a double bond because this lone pair went here. And then that would get deprotonated. So your final answer would look like this, a nitrogen with a double bond and the R group. So these are very similar. I mean, the only thing that was different was where the substituents are, but I still go through the process of drawing it all the way out because it's just difficult for me to go through that without doing every step. Like the protonations, I'll skip over, but I really have to do every step to know what happens as the final product. I use my arrows to predict the final reaction, not really the other way around. Okay, so the next one is actually all of these reactions are in equilibrium. So these arrows weren't quite right. It should have been, like this. So if you do any thing that reacted with a ketone in the presence of acid to make something else, like a hemiacetal, an acetal, an imine, and enamine, in the presence of acid is actually going to reverse itself. So this is an imine. So I know that imines, the nitrogen, the overall reaction for an imine is it goes from this to this, right? Like I just know that, we've gone over it a lot. So I'm seeing this in our group right here and knowing like, oh, I think that probably formed from this and this in the presence of acid. So that's how I would go about that reaction. If you're not sure, you can then do the reverse and be like, okay, if this attacked here and went like this, what would happen? But this is technically a reversible reaction. And I haven't talked about that yet, so I'm glad that this one brought it up. And then the same thing with this. So this, we did the rainy nickel, which is similar, but if you have a ketone in the presence of an alcohol, it will make an acetal, right? So this will attack and this will eventually leave as water and you'll get something like this. But if you add this to acid, it will revert back to the alcohol and the ketone. All these reactions are reversible. So I see this and this looks like an acetal. When I first saw this question, I assumed it was like this, and that then they had just done like something that looked like that. And then I realized that didn't make sense. And actually, they tricked us. And the ketone that gets two oxygens bonded to it that turns into the acetal is right there. So I was like, this doesn't make sense. You can't have 5 rings to carbon and like this ketone won't work. The initial starting material was this plus a very weird looking diol. So if you combine these two things in the presence of acid, these will act in the exact same way as this. This is the same exact thing, just makes a 6-membered ring instead of a 5-membered ring and will protect here. It's the same, it'll attack here and kick up just like we saw with the thioacetal formation. So if you're not sure why, you can work backwards here, but that's what I look for on these is I look for what carbon has 2 oxygens bonded to it because that's where the ketone originally was. So this next one, this is also an imine formation, it looks like, because this is a not a secondary amine. It's not a primary either. It's just NH2. So I think it would, I'm bad at drawing 7-membered rings, basically end up like this. But the first step, O minus, NH3 plus, it will get protonated 2 times and do OH2 plus, and this would be NH2. This would come down, kick this out, and you'd get NH2 plus. That would be deprotonated, and you'd end up with this. This is a secondary amine, so it would make an enamine, not an imine. So, but even if you don't know that, you can just go through the steps. This would attack and kick up, and you'd end up with, there is not enough space on this page. a nitrogen with a hydrogen there, and the double bond, or the lone pair has actually bonded here to this 5-membered ring with an O minus, and then you've got this over here. This is a minus charge, not a methyl group. And then this is a positively charged, so this will come take that proton, and you'll get, I'm running out of space. So sorry. You'll get, let me get you a fresh piece of paper. Okay. So this attacked here, this kicked up, and the protonation step happened. So we have a nitrogen that's been deprotonated, bonded to, so it has a lone pair, bonded to a 5-membered ring with an OH on it. This would get protonated again to become OH2 plus from this acid right here in solution. Then this would come up here and kick this out, and we would get a nitrogen that has 2 bonds to this 5-membered ring. However, that makes this nitrogen positive, which it's not happy about. So hydrogen will be taken from, let's see, 1, 2, 3, 4. It could go from here or here. Either one of those would be appropriate. So it'd probably come from this one, and it would be the water in the solution could come, take this, put this here, and go up, and you'd end up with a double bond on either side. They're identical, so it doesn't matter, with a nitrogen. Oh, no, sorry. I did that wrong. It's one away right here. And then, wait, no. Am I losing it? It's too late at night for me to be doing this, I think. I am losing it. I took the hydrogen from the wrong ring. I'm really losing it totally and completely. So what happens is the hydrogen comes from here, a double bond forms there, and this kicks up. I don't know what I was thinking. I'm losing it. So this is your final answer. You would have a double bond one away. So sorry, I'm having a hard time today, clearly. I'm doing a lot of videos, one right after another, so maybe that's it. Sorry again. So this should be your final answer on this one. Okay, the next one is Baeyer-Villiger oxidation. So with Baeyer-Villiger oxidation, the big thing is a hydrogen moves more easily than a phenyl. And after that, it's by like more substituted to less. So like tertiary, secondary, primary. So here we have a tertiary on one side and a secondary on the other. So the oxygen just inserts itself. This is what's known as migratory aptitude. So this is easier to migrate than this. And it just inserts itself and you get an ester. So that's all Baeyer-Villiger oxidation is it just literally, you know this chart, so you have to know where it's most likely to put the oxygen in, and you just go with that. So again, and this is a peroxy acid that has Baeyer-Villiger oxidation. So you have to add that to your portfolio, right? Like before, if you saw peroxy acids, MCPBA, or anything with 3 oxygens there, you would say, oh, I know what this is. This is going to make an epoxide. But now we have Baeyer-Villiger oxidation can form as a result of this. So you have to ask yourself, is there a double bond where an epoxide can form, or is there a ketone? If it's epoxide, there will be a double bond. If it's a Baeyer-Villiger oxidation, it'll be a ketone. Those are, or a aldehyde, basically a carbonyl carbon. Those are your options. So for this one, we have, let's see, 1, 2, 3. That has 4 substitutions, and this has, that's a tertiary, so it would go on the other side. So it becomes a 6-membered ring. And it does not replace the oxygen. It literally inserts, or the carbon, it literally inserts between the two. So this 5-membered ring became a 6-membered ring, or this like 3-carbon chain now is a 4-carbon chain. It adds an oxygen in between the two, and you do not need to know the mechanism for that. Here's another one, another peroxy acid. Remember, it's hydrogen, then phenyl, And then after that, it's like tertiary, secondary, primary, basically more substituted to less. But it's hydrogen, phenyl, and then the alkanes. So hydrogen is first. Hydrogen is the most easy to migrate, so makes a carboxylic acid. So you've now learned a new way to make an ester and a new way to make a carboxylic acid with that. Okay, now these are retrosynthesis questions, and when I'm looking at this, I'm seeing that there's a new carbon-carbon bond formed, like there's a new methyl added, and that can only happen with Grignard, but Grignard is not going to go well with an alcohol. So you have to think to yourself, like, what do Grignards normally attack to make alcohols? Well, they attack ketones or aldehydes or esters. And in this case, we have a secondary alcohol, so we can use any oxidizing agent, KMNO4, PCCC, Jones reagent, any of those, to turn this into this. And then you can do a Grignard reagent, that's CH3 MgBr. Remember, because Grignards are really good at making new carbon-carbon single bonds. And the only way you've learned to make a carbon-carbon double bond is with the Wittig reaction. So, but we want a carbon-carbon single bond. So that's going to be a Grignard, and that would make this O- with the CH3. So it looks like that would work, and then we need H+. So to get from A to B, you would need, or to get from here to here, you would need an oxidizing agent. Anyone would work. Jones, PCC, or KMNO4. KMNO4 wouldn't work if there's double bonds, remember? It cleaves double bonds, but there's not a double bond here, so it doesn't matter. And then you would need a Grignard reagent. And then you'd need an acid to turn that into an alcohol. And so then I see this next one's very similar. It adds a methyl group right here. So we're probably going to go through something similar, but this is a primary alcohol. And this is a really good chance for you to review for the final. There's only one oxidizing agent that can take a primary alcohol to an aldehyde, because the other ones will keep oxidizing. So if you have a primary alcohol, it will become an aldehyde, and then another oxygen will be inserted here, and you'll get a carboxylic acid. One will stop here, and two will go all the way to here. So I'm going to pause and see if you get a chance to remember. PCC is the only one that will stop. Jones and KMNO4 will both go all the way. It didn't matter here because it was secondary, but on a primary one, you have to use PCC so that it will stop. And then you can actually do the same thing for the next step. You can use a Grignard reagent and then acid. So for this one, you would use PCC followed by the same Grignard reagent, actually. Sorry, I keep running out of space. And then acid. So I hope that was helpful to you. Sorry, I got a little confused on the Wittig and on that one enamine question. My brain's a little foggy today. Didn't sleep great last night. So if you have any questions or if you want to clarify anything, please feel free to reach out to me or Dr. Corrales. And yeah, good luck on your quiz.